Good morning, everyone. In this lecture, we'll see how the structure is been analyzed and what is the impedance matching and how this is how it is going to be used for the effective parameter analysis.
This is the perspective view within specification. So we have, as I have discussed, told that there is a two hexagonal ring. So this two hexagonal ring is placed in the bottom of the structure, and then it's placed on the top of the structure with an air gap, and which both are connected with the electromagnetic wire. So here this structure is operate and the frequency of 2.45, and it is the substrate which we have used as an FR4 substrate with an height is of 1.6 mm, and then permittivity is in 4.4, and this total size of the structure is in 1 point, that is 18 mm, and we have used this radius. The radius is of 16 mm, the difference from the center point to this edge of the string, and then is the thickness between this ring is of 2d, d is like 2 mm, and what this height between the structure and then top of the substrate and the top of the hexagonal ring is of 1 mm. So totally this 1.6 plus 1, so that is of 1.5 mm, so that is of 2.1 mm structure. So this is to better understand, we have made this unit cell into this model into the equivalent circuit model. The metal line is act as an inductor, and then gap between the strings which it can be act as a capacitor. So the structure will behave like an LC resonance circuit, and then resonance frequencies derived using the standard inductors and capacitor formula, and it matches with the result. So here the structure is made of this two ring is made up of this inductance and then capacitance. So the frequency is calculated with this L1, C1 and L2, C2, and there is a mutual coupling capacitor as in CM. So the L1 is nothing but L1 is calculated based on this mu naught A. A is nothing but the area of hexagonal ring. A into 1.5 minus ln of 8A by H by L. H is the height of the substrate, L is the length of the unit cell, and then capacitance C1 is calculated based on this epsilon R A by L. So here C1 and C2 is almost of same. This based on this area of an hexagonal ring we have used to calculate this C1 and C2 value. And then area A is nothing. How we have calculated A is equal to radius of R plus L by 2, which is the area of unit cell of hexagonal structure, and then length of the substrate. So and L2 is calculated based on this mu naught mu R by pi into cos h of h. This h is the height of the substrate, and h dash is the height between this air gap between the top of the substrate and then hexagonal ring, and divided by this radius of the structure. And cm is like we called as a coupling gap structure. This coupling gap is nothing but air gap. So that air gap is called, we have an air gap. So we made this structure, we made that as a capacitance thing. That is Cm is equal to epsilon r into d by h dash. So where this permeability is, we can call as a free space, and then mu naught and mu r. The radius on this and the height of the metal wires is denoted as an h plus h dash and then r, and there is a mutual coupling capacitance between this top of the substrate as Cm, which is run as a three hexagonal ring, and we have made this C1 and C2 is almost of same. So here you can see this is a effective parameter extraction value of an L1, L2, C1 and C2, and then Cm. Next is the result and discussion. So in results and discussion, we can see here is an graph, a transmission coefficient graph of 3D MTM structure. Here you can see this we have analyzed with the different air gaps between the top of the substrate and the hexagonal ring, different air gaps. So we in which the based on this air gap which is resonating at this proposed 2.45 gigahertz, we have taken that has been fixed with the air gap of 1 mm. So this graph shows us is S21 now for transmission coefficient, and which it clearly indicates that it resonates at this S21. At this point, the S11 is false as 0, which I have not shown here, which it indicating that this is a perfect impedance matching. And there is an band gap of 2.3 to 2.57 gigahertz, which it has been used at the ideal for an IoT bands. And this at the resonance, the reflection is 0. The metal lines and split gaps in height or plays the crucial role and important properties of defining, making them to be implemented in the resonating at the particular band gap. Next is the 3D S parameters of, in last slide I have shown the S parameters of S21 parameter. Here I have shown the clearly indicating all the parameters of EM simulation and S11 and S21 parameters. So here you can see it is resonating at 2.45 gigahertz and S11 is also 0. And I have shown both this equivalent circuit and EM simulation circuit simulation are matching at the exactly resonating at the same resonant frequency. And I have made the structure to be optimized with respect to this what is it, air gap. Based on this height of this H dash, I have made the structure to be resonating here. Here you can see this how the height of this 3D MTM has been optimized. And so this to validate the structure and making for the maximum gain and coupling, we have used this different structure height analysis and circuit analysis structure. Next is the we are showing the effective parameters of unit cell structure. So which we have already discussed that unit cell parameters is based on the permittivity and permeability. For that resonance structure, how we have achieved the negative permittivity with respect to this respect to this band gap. Here you can see this of approximately of minus 40. Similarly, the negative permeability is also minus approximately of 30 to 40. And here you can see the refractive index, which is also resonating at the negative refractive index. And here all this negative refractive index parameters are extracted from this NRW, that is Nicholas Weir method. This method is for extracted based on this S parameter. So based on this reflection coefficient and transmission coefficient, we have calculated the permittivity and then permeability and then refractive index. So this refractive index structures show this value. So almost confirm that permittivity is ranging from 38 to 40 and permeability is from 33 to 40 minus 33 to minus 40, and effective refractive index is of minus 42 at, which is at 2.45 gigahertz. So which it confirms that this structure is a double negative medium structure. Next is the current distribution. This current distribution image shows that is how the energy has been flowing across the unit cell structure. So this electric field along the ring causes the current loops, so which it generates the magnetic field. So this field interactions is what we create the negative permeability, and then refractive index. So based on this, there is a strong current reversal is visible, which is indicating there is an intense of internal coupling. So this is what is the current distribution, how we get it, and based on this, how we have achieved the compactness of 3D metamaterial is calculated based on the effective medium ratio. This effective medium ratio is calculated based on the length of the unit cell and then the wavelength of the 3D metamaterial hexagonal metamaterial structure. So this the value which is EMR is achieved is 12.12 for an unit cell dimension for the dimension of 18 cross 18 into 1.6 mm at a giga at 2.45 gigahertz. Ideally, we say this if the EMR value is greater than threshold value is greater than 4, the unit cell is exhibiting the characteristics of negative permittivity, permeability, and then negative refractive index. And even if this when the EMR value is greater than 4, that means that our structure has been achieved the compactness in the metamaterial. Next is the conclusion that we have designed the novel 3D unit cell structure, which it exhibits the double DNG material behavior, and it operates at 2.45 gigahertz, which is fit for the ideal IoT applications. And then we have achieved the refractive index of -42 and then EMR value of 12.12, which is indicating the compact efficient design. So this design can be offered for the used for them various applications. So this unit cell structure is a not an thing. This unit structure can be made as an array of an unit cell, and this that array of unit cell can be deployed on any applications. Like for example, we can use an super substrate, which it can help us to improve the beam gain, or else like for the beam steering and for energy harvesting, and then multiband operations. So these are the things where we can use for this using this unit cell structures. These are some of the references which we have been used in the article, and then based on this references, we have designed the unit cell structures. Thank you.
Thanks for watching. So far we have discussed about the metamaterials and metamaterials usage, and how this is going to be useful as an application for if we go use for an different wireless applications. Thank you.